Hello and welcome back to the course on deep natural language processing, and today we're finally talking about the sequence-to-sequence model, and we're going to be discussing its architecture. Alright, so where did we stop last time? Last time we stopped here where we were talking about the bag of words model. As you can see here on the right, we've got our bag, and we discussed that there's at least two ways that you can go about it once you've got your 20,000 elements long representations of your sentences or of your emails, and you have all this training data. You can feed it into a non-deep learning model such as logistic regression, and that will give you an NLP algorithm over here, or you can feed it into a neural network, or meaning a deep learning algorithm, deep learning model, and that will give you a deep natural language processing model over here. So both a bag of words, but different types of bags of words. We said that there's at least one drawback, one limitation, and that is that this approach just gives you a yes-no response. Yes-no type of response. It's a good start, but at the same time, it's not going to get you very far if you're trying to build a chatbot. You want to chat to people, not just say yes or no to any kind of question or sentence they're saying. You want to have a meaningful conversation. So let's have a look at some of the other limitations. Issues with the bag of words model that make it undesirable for a chatbot project. Number one is fixed sized input. So if we go back over here, you'll see that every single time we have to have the same type of input, same length of input for this training to go well. Because on one hand, if we feed into logistic regression, we want to be sure that the features are in the right columns, in the right places, and then among the training data and the verification data, or the actual data that we want to get a result for. So that's the limitation. That's why we have the 20,000 element long. It can't be shorter or longer. It has to be that limit, that size. And also in the input layer for the neural network, same thing. You've got like a certain number of neurons. You've got to feed in the right words in the right spots into this neural network. You can't mix them up. You can't have a different size in order for it to work. So that's the limitation, fixed sized inputs. Second limitation, it doesn't take word order into account. Interesting. So what does that mean? Well, if we look back, again, jumping back to this slide over here, if we look back over here, you'll notice that we're just counting each occurrence of each word, rather than looking at not just occurrences but also where they are placed. So for instance, if you jumble up this email, or the words in this email, you will still have the same representation. And like we all know that if we change around words in a sentence, they can change the meaning. For instance, let's say, for example, is the cat shorter than the dog? Right? That's one sentence, and the answer might be yes. Usually cats are shorter than dogs, and let's say we have an example that a cat is shorter. Is the cat shorter than the dog? If you just change the cat and the dog, those two words around, then it becomes, is the dog shorter than the cat? Exactly same words, completely opposite meaning, and the answer in that case would be no. And so you can come up with examples where if you jumble up text in the emails, words in the emails, even though the representation will be the same, your answer would have changed from yes to no, but the model is going to give you the same answer. So that's a significant limitation. That basically what's happening is loss of information. We're losing information through the bag of words model just through the way it's constructed, because we're not taking into account position of the words. So fixed size input doesn't take word order into account. And the third one is what we talked about already, fixed size output. In this case, it's just one word, yes or no. But basically that not only yes or no, we could come up with a more like a longer output, multiple words, but it won't be variable. That's kind of like an even stronger statement, that we don't just want yes no, like even if we have more options than yes, no, we might have like 5 options or something like that, or they might be longer. But what we want is we want variable sized output. So depending on what we were asked, we want to be able to say a sentence of maybe 5 words or 50 words. It should be totally up to us. The model should be flexible to give out a response, not just limited to whatever number of words. It can be like a short response, it can be a long response. Just like as humans, when we talk, we don't limit ourselves to we have to answer with 5 words or we have to answer with 10 words. It has to be variable. So those are the main limitations. Fixed sized input doesn't take word order into account, and fixed sized output, the limitations of the bag of words model. So the question is, what are we going to do? How are we going to solve this puzzle and overcome all of these limitations? And the answer is RNNs, recurrent neural networks. So if you haven't had a look at the annex for this course on artificial neural networks and recurrent neural networks, now would be a great time to look at it and get into this space, understand what recurrent neural networks are and how they work, what they're constructed of, different types and so on, what backpropagation is, stochastic gradient descent and so on. There's lots and lots of concepts that are going to be assumed going forward, that you are up to date with them, you know what they are in the future tutorials starting from now and further down in this course. So if you haven't looked at the annex, highly recommend to stop this video now and look at the annex. But otherwise, let's proceed. All right, so this, like if you've seen the annex for the recurrent neural networks, this is what Andrei Karpathy has come up with in his blog on GitHub of the different types of recurrent neural network architectures that you can come up with. And just as a reminder, recurrent neural networks, here every single box is not actually one cell, it's actually a whole layer of neurons. A whole layer of neurons is represented by every single box. Just here what we're looking at is the unraveled neural network and the unraveled time loop of the recurrent neural network. So this is the neural network feeding into itself through time. Like each one is a different neural network, of course, but it's feeding itself into itself through time. But if you look at it like from the top, actually here, like it's going into the image, you've got a whole layer of neurons. Like it's a 3-dimensional image, that's why you can't see it. That's the way I imagine it. We've got a whole layer. Everywhere is a layer of neurons. So one way is like layer, layer, layer. Another one is, okay, so one layer and then one to many. So they actually have titles at top. Many to one, so you have many and then you come down at one. You have many to many and many to many this way. So right away, just based on what we're trying to build here, we want a variable sized input and variable sized output. So 1 to 1 wouldn't work for us. 1 to many wouldn't work for us because we don't have just one word as an input. So we're actually going to put words into each cell. It will make sense as we go along. It will definitely make sense how all of this works. But for now, the way we're going to look at it, so this one won't work, this one won't work, this one won't work because it's just 1, 1, 1. We want more, like this is kind of like if we have a yes no response, this could work for us, but we want more than one response. So we're left with one of these two options, a neural network with many to many like this or many to many like this. And the one we're going to go with is this one, and the reason for that is because we not necessarily will have always the same size input and the same size output. So if somebody asks us a question of 5 words, not necessarily we'll have 5 words as an answer. So that's why we want a variable to variable input and output, but they might be different. So that's like a short excursus into what type of neural network architecture we're going to be aiming for. It's going to be that one. But now let's jump back to our text, and it'll all make much more sense from there. So there's our 20,000 element long vector, which we use for the bag of words, and we're going to just throw it away because we don't need it. In fact, we're actually going to shorten this sentence. It's not something that's part of the algorithm. Of course, we can work with any length sentences and emails and so on, but just for simplicity's sake, for us to look at the whole picture and be able to grasp it, we're going to shorten it, and that's just for the educational purposes. Again, this algorithm works for any length question or email or chat, whatever we're creating. And so, yeah, so what we're going to do is we're going to take these words, each single word, including the comma and the full stop, and we're going to code them. So we're going to create a different vector. This time it's not 20,000 symbols. It's just going to have words. So like one way to create it is we take those, from that big vector of 20,000, we just take the position of every word. So let's say hello was on position 5. So we're going to put a 5 here. Kirill doesn't have a position in that 20,000 vector, so we're just going to put a 0 because one of those non-English words. Comma had position 9, so we're going to put a 9. Checking, 23. So instead of counting the recurrence of every word, we're creating a vector which is as long as our vector, as long as our sentence plus an a start of sentence over here, start of sentence, end of sentence, at the start and beginning, and they, as we remember, they have reserved numbers, so this one's always going to be a 1, this one's always going to be a 2, and then for every element we're just replacing the word with the actual numerical version of the word, the number that's, or the position that's associated with that word. So like for instance, if you had two of the same words, if you had if and if, you'd have a 7 and another 7, or you had like a comma and another comma, you'd have a 9 and another 9. So that's totally fine, and this is how we construct this vector. And so as you can see, the size, the length of this vector will depend on how many words we have in our email, how long our email is.